Hello, let's start with our new lecture. In this lecture, we will talk about the equivalence of context-free grammars and push-down automata model. Equivalence of CFG and PDA models. We had actually in the start of our discussion regarding context-free languages, we first tried to describe context-free languages using the context-free grammar model, and then later on we talked about the push-down automata model, and we have provided several machines for given context-free languages, but we never talked about the actual equivalence of these two models in terms of their capabilities, both of their capabilities to describe context-free languages. For this equivalence, we have actually two sides to consider. One is that given a context-free grammar, we should be able to construct a PDA that is equivalent to it. And in the other direction, given a PDA, we should be able to construct a context-free grammar that is equivalent to it. Let's first start with the first direction, going from context-free grammar to push-down automata. For this, we will try to provide an algorithm that describes the main steps for given a context-free grammar to convert it to an equivalent PDA. The main idea or the main thing we need to consider is, remember that with a context-free grammar, we start with our starting variable s, and we do a sequence of derivations, and then at the end we arrive at a string that is generated by the given grammar. And since there is non-determinism in the nature of the context-free grammars, we can actually follow many different possible derivations to arrive at a string. And if we can somehow, using our PDA model, if we can simulate all possible derivations using the PDA model, then we should be close to simulating the derivations of a given context-free grammar using the PDA model. So the main question is how to simulate all possible derivations. We can pick one of the derivation types, either leftmost or rightmost. Let's say all possible leftmost derivations of a given grammar, of a given context-free grammar with a PDA. So this is the main question. Let's try to visualize how a sample derivation of in a context-free grammar looks like. We start with our starting variable s, and then we replace s with, let's say, one of the rules given by the grammar of that we can extend our variable s with. So we continue with those derivations. We can have many intermediate strings in here. So let's say one string is 0, a, s, 0, and then we doing leftmost derivations. Next we can expand this variable a, and instead of that a, we can write the right hand side, the string corresponding to the right hand side rule of a. So it would be 0, that string followed by s followed by 0, and then do another step and so on. And at the end of our derivation sequence, we could arrive at our string, let's say 0, 0, 1, 0. Note that there may be many different derivations that lead to this string 0, even if we use leftmost derivations, especially if the given grammar is unambiguous. So how can we simulate such a derivation sequence? The main idea is to be able to make efficient use of our stacks, which are available for our use in the PDA model. What we will try to do is, in our stack, in the stack for the PDA, we will try to keep any intermediate string that is possible in a derivation sequence in the stack. Okay, so the idea is the following. In stack, keep the current intermediate derived string. So this is one part of the main idea. So we will basically keep such a string in our stack. And how does normally in a PDA we have our input tape, and each time we process an input symbol from the input string. How does the processing happen of processing of these input symbols happen within this simulation is that each time we will try to check the symbol that appears at the top of the stack. Now, since we will be keeping such intermediate strings in our stack, there are two possibilities for the top of the stack. If the top of the stack is a terminal, just like this one, so if this was the intermediate string that we record in our stack currently, our top of stack would be corresponding to this terminal 0. If top of stack is a terminal, what we'll try to do is we'll try to match this terminal at the top of the stack with the current symbol under the tape head. Let's say this is our input string, and it could be the case that the tape head is on the first symbol 0. If this is the case, we can match this 0 in our intermediate derived string with the current symbol that we want to process in our input string. So if this is the case, then match top of stack terminal or top of stack symbol with current input symbol. This is one case. Remember that the second case, it could be the case that instead of this terminal, we might have, if we didn't have this terminal, if we had this intermediate string with AS0, A would be, the variable A would be on the top of the stack. So top of stack can be a variable as well. If top of stack is a variable, what should we do in that case? Since we want to kind of simulate this as a sample derivation sequence for our grammar, if there is a variable A, we need to be able to, with our single transition in the PDA, we need to be able to derive the following sequence. And how is the following sequence derived? By, normally in a derivation sequence for a grammar, given the variable A, we basically extend the given variable A with one of the rules of our grammar that corresponds to A. Okay, so we can do the same thing in our simulation using the PDA as well. If top of the stack is a variable, let's say A, we can, since we want to represent this next intermediate stack, this next intermediate string in our stack as well, we can, instead of A, write down whatever the right hand rule we want to use in our derivation into our stack as well. Okay, so if top of stack is a variable, then we will expand, if this is the case, expand variable with one of its rules. Expanding variable with one of its rules in terms of our PDA corresponds to removing that variable from the top of the stack, and instead of that variable, pushing the one of the right hand side rules, basically a string on the right hand side of that variable, into our stack. Note that for a given variable, we might have many alternative rules for the right hand sides, and we should be able to, that corresponds to possible alternative derivation sequences. Now we should be able to simulate all of these possible derivation sequences using the PDA, but that's going to be simple with the PDA model because we can make use of non-determinism at this point. So expand variable with one of its rules non-deterministically. So basically, non-deterministically make the expansion for every possible rule that is given for the given variable a. So this basically summarizes the main idea. We can actually figuratively show this main idea with our PDA model as well. Actually, in our conversion algorithm, for any given context-free grammar, the format of the simulating PDA will be the same. Okay, so this is the main format that we are going to have. We'll have our initial starting state, let's call it Q1. Our initial transition will be, don't read anything from the input, don't pop anything from the stack, push the starting variable of the grammar S and a $, the usual delimiter that we use to check the empty stack condition. Okay, so this is going to be the first operation that we do in every PDA that is simulating any given grammar. We go to a new state, Q2. We do this for the first step of the derivation. Remember that all of our derivations start with the variable s and then they follow a sequence. So the first variable that we have is our s, the starting variable s. Remember the main idea that we just described. Each time, now what we do is at each transition we will keep on doing the following. Pop the top of the stack symbol. If it is a variable, then non-deterministically expand that variable with one of its right hand side rules. So let's first, so we will, since this is going to be repeated for every derivation step, we need to do this within a loop. So for every variable that we have in our grammar, every variable a, for every variable a with a rule that says a can be expanded with some string alpha, introduce in here within this loop, introduce a transition of the following form: epsilon a alpha. The meaning of this transition is that don't consume any input symbol, pop a from the stack, remove a, the variable a from the stack. Instead of a, write down one of its right hand side rules, basically a string alpha. This corresponds to one step in our derivation sequence where we basically expand the variable a with the string alpha. The other case is, it could be the case that on top of the stack there is a terminal. So for every terminal in our input alphabet, in our input alphabet sigma, we will write down a transition. Again, within this loop we will have a transition of the following form: a comma a right arrow epsilon. The meaning of such a transition will be that consume a from the input string and remove, pop a from the top of the stack and don't push anything into the stack. This will these transitions will be the transitions where we keep on processing the input string symbols. Okay, and at the end, if we arrive at a configuration where the stack becomes empty and the processing of the whole input string is finished, then we need to accept the given string. So we will have a transition from Q2 that says epsilon $epsilon Basically, the input string is finished. We read epsilon from the input string. Our stack is empty because we are popping a dollar, the special delimiter we had pushed at the beginning, and don't push anything into the stack. In this case, go to the accepting state. Let's call it Q3. Now, this will be the format, the general format of every simulating PDA, every PDA that simulates a given context-free grammar. What will change from different CFG to different CFG is that it's going to be basically these sets of these transitions that we have corresponding to the rules that we have in our given context-free grammar. To make this a bit more clear, let's try to do an example. This conversion algorithm. Let's say that we are given the following grammar. Given grammar S goes to 0S or 1A, A goes to epsilon or 0A or 1A. Actually, in today's live discussion session, we had talked about this grammar already, this context-free grammar. Just to remind you what language this grammar recognizes, let's try to see what it does. Let's take the variable A. Epsilon is the base case. Basically, empty string is in the language that is generated by this variable A. And it has two other rules, 0A, 1A. The string may start with 0 and can be followed by the variable A itself. It may start with 1 and may be followed with the variable itself. Then we can see that this part of the grammar or the variable A generates all strings defined on zeros and ones. Basically any string. Now if we inspect the variable S, it says it has a rule that says 1A. Remember that A corresponds to any string and we are attaching a 1 at the beginning, or we have a 0 and followed by the string, the variable S itself. So basically we can see that S corresponds to all strings where we have at least one symbol 1 in it. Because A corresponds to anything and we are having a 1 at the beginning, this will generate all strings with at least one 1. Let's start with a 1. And 0S, if S truly generates all strings with at least one 1, then 0S basically generates all strings with at least one 1 that start with a 0. Both of these cases basically handle all possible cases. So in parentheses, we can simply type down the language that it generates. Basically L is equal to W in 0, 1 star, such that W has at least one symbol 1. So this is just in parentheses. But our goal, remember, was to, using our conversion algorithm, to convert this given grammar CFG into an equivalent PDA. We will use this general format. So we have our starting state Q1, epsilon, epsilon, and S and dollar, starting variable followed by our special delimiter dollar. And this is our Q2. And we have our loop, which will have many transitions. Mainly two types of transitions that are related to the variables in our grammar and transitions related to our terminals in the grammar. Let's first write down the transitions related to the variables. So remember that for every variable A in the grammar, we need to write a transition of the following form: epsilon A alpha, where A alpha is a rule in our grammar. Okay, so let's first take A for instance. Let's start with S for instance. For S we have two rules. S may expand to 0s corresponding to this rule, we will write a transition of the following form: epsilon s, and into the stack push 0s. This is one transition corresponding to this rule. Corresponding to the second rule, s goes to 1a, epsilon s into the stack, let's push 1a. Let's do the same things for the variable a. Epsilon a, the right hand side might be epsilon. Epsilon a, the right hand side might be 0a. Epsilon a, the right hand side might be 1a. Now these are the transitions corresponding to our variables and their rules of expansion. Finally, we need to have transitions corresponding to our terminals. We have two types of terminals, zeros or ones. If we see a 0 in our string, in our input string, and the top of the stack is a 0, we basically don't push anything into the stack, epsilon. If we see a 1 and our top of stack is a 1, again epsilon. So all these transitions are within a loop. And finally, we need to have our final transition going into the accepting state, Q3. This will happen when the input string is finished processing, epsilon from the input string basically, and our special dollar delimiter indicating the empty stack condition, and don't push anything into the stack. To be able to have a clear picture of whether how this given PDA simulates this given grammar, let's try to concentrate on this PDA, the simulating PDA, and let's try to see how it works on a given string that belongs to this language, basically that is generated by this grammar. That should make the simulation idea more clear. Let me redraw the simulating PDA, Q1, epsilon, epsilon, and going to S dollar, and Q2 within a loop. We have 0, 0, epsilon, 1, 1, epsilon, corresponding to terminals, and then we had for the variables, epsilon s goes to 0s, epsilon s goes to 1a, epsilon a going to epsilon, epsilon a going to 0a, epsilon a going to 1a. These were the transitions corresponding to our variables and our accepting state Q3, where we go there with the transition epsilon dollar epsilon. Let's see how the simulating PDA works on a sample string. Let's say our sample string is w equals 0, 1, and 1. Okay. According to the rules of our grammar, such a string should be accepted. Okay, 0, 1, 1 should be accepted by this grammar. How would a sample derivation sequence be? We would start with s. Remember that we want to derive the string 0, 1, 1. We would expand s with this string 0s. Next, we would take this s and expand it with 1a. Next, we would take this a and expand it with yet another 1a, and this a would be expanded with epsilon, and we would arrive at our string 0, 1, 1. Let's see how such a derivation sequence is simulated in our simulating PDA. We will try to show the computations of this PDA on this given input string. Initially, we start as usual with an empty stack, and we definitely need to take this first transition. After this first transition, let's see how the stack looks like. We will have pushed our dollar delimiter, and we will have pushed s into our stack. Let's show our input string 0, 1, 1. the input tape head will be on the first symbol because this initial transition doesn't consume anything from the input string. It consumes simply epsilon. After this initial transition, we will be at state Q2. At state Q2, the tape head will be on the initial 0, and this will be the configuration of our stack. Now, for the rest of the simulation, we will keep on taking these transitions to do the derivations that correspond to deriving this string via our context-free grammar. Let's see what happens within these transitions. So our top of stack is a variable, which means that we cannot take these two transitions because they expect, each of the transitions expects the top of the stack to be a terminal. Since top of the stack is variable s, we can take either this transition or this transition. Okay, so in our computation tree, one branch will lead to the following configuration. This is $, and then s will be replaced with, let's say, with the right side with 0s. In that case, we'll have s and 0. So this will be the configuration of our stack. This s is replaced with its right hand side rule 0s. Note that since the stack works in a LIFO principle, we will first push s into the stack and then next push the next symbol, which is 0. For the other possible transition, we will do this transition. So the configuration of the stack will be as follows. We have $, at the beginning as usual. S will be removed, will be popped from the top of the stack, and instead will be replaced with 1a. We will first have a, and then on top of the stack we'll have the symbol 1. Okay. In both of the cases, in both of these transitions, we read epsilon from the input tape. So 0, 1, 1, and the input tape head is still on 0, 0, 1, 1, and the input tape head is still on 0. We are still at Q2, so I won't write that. Our state doesn't change. Now let's see both of these computation branches. Regarding the right branch, now the input tape head, under the tape head we have 0. On top of the stack we have a 1. There is no transition that we can take that is possible for this configuration, because among the terminal transitions we expect the input symbol we read to be the same as the top of the stack, the terminal stored at the top of the stack. Okay, but in this case the symbol read is 0, top of the stack is a 1. So this branch dies out in here. So we can continue with the left branch. We can take basically this initial transition that says process the input symbol 0 under the tape head from the input and pop 0 from the top of the stack. Don't push anything into the stack. If you follow this transition, this will be the current configuration. In our stack, we will have $delimiter and we will have s as variable. 0 is already popped. 0, 1, 1. Our tape head is now on the next symbol 1. Again, we are at state Q2. According to this configuration, let's see what transitions, among the possible transitions, what transitions can we take. Now, top of stack is a variable and it's s, so we can take again one of these two transitions. Okay, so again we will have two branches. In one of the branches, let's say we do the first one, epsilon s 0s. S will be popped from the top of the stack, this is what it says, and instead we push 0s onto the stack. So we have $, and then to push 0s we first push s and then we push 0 on the stack. And corresponding to this right branch, let's do this transition. Again, our tape head position doesn't change. Corresponding to this next possible transition, s is removed and instead 1a is pushed into the stack. So we have $a and we have the symbol 1, and our input tape head is still on the symbol 1. Okay. Now again, inspecting these two possible configurations, now we see that our top of stack is a terminal 0, and under the tape head we have the opposite symbol. So according to these two transitions related to terminals, we cannot proceed with this configuration. So this branch, this computation branch, dies out in here. Okay. With respect to this configuration, our next step would be to consume the symbol 1 from the input and to pop the symbol 1 from the top of the stack symbol, okay, which is the intermediate derived string. So after this, we would have the following configuration in our stack: $, and A. So 1 is simply removed, 0, 1, 1. Our tape head moves 1 position to the right by 1. I'm not going to show the rest of the computation tree, but you can imagine, you can see that as we go along this computation tree, our transitions that we commit at this looping stage Q2 are actually doing the derivation of our grammar. So we start with S, and then this is the target string that we want to generate. We expand, so let's try to show the derivation corresponding to this branch of our tree. So far we start with S at the beginning, and then next we expand S with the rule that says you can expand S with 0S. So S is expanded with 0S with this computation branch. Next, what we can do is take the, so for the next step, well, we are consuming an input symbol, but this is not, this we don't immediately show in our derivation. Next, we can take this S and expand it with one of the rules, again with 1A. So we have 0, this initial 0 is matched with our initial 0 of our input string. Next, S is expanded with this rule 1A. So far these 1, 2, 3, 4 steps of our computation path has done this part of the derivation, and with this computation path we have been able to match from our target string, we have been able to match the initial 0 and the second symbol 1 as well. So if we were to continue with our computation path in here, we would be able to expand next A with the proper, with several branches. We would be expanding A with any of its right hand side rules, okay, but the successful rule will be this one. So we would be expanding 0, 1, A with 1A, and finally A would be expanded with epsilon, and we would arrive at 0, 1, 1. These two parts I haven't been able to show in here due to lack of space, but you can do it as an exercise to verify that constructing this computation tree further, you can actually simulate these two derivation steps as well, just the way that we have constructed this part of the computation tree.